Welcome back. Today we are going to dive deep into the world of resistors. You have probably encountered resistors in countless devices, from your home appliances to advanced electronics. Today we learn about the two main types of resistors and how the temperature affects their behavior. Resistors are used to control the flow of electric current in a circuit, and they come in two types: carbon resistors and wire wound resistors. Let's start with wire wound resistors. Wire wound resistors are made by winding a resistance wire like manganese, constantan, or nichrome around an insulating cylinder. These resistors are very accurate and can handle high power levels than carbon resistors, making them ideal for high precision applications. On the other hand, carbon resistors are made by molding carbon along with a binding agent like a cylindrical shape. Wire leads are then attached to the cylinder, allowing the resistor to be connected to a circuit. These are typically used in everyday electronic devices because they are inexpensive and can handle a variety of resistance value. Resistance are color coded to give their values. R is equal to AB into 10 to the power C ohm D, where A, B, C are colored strip. Here, the first two colors A, B indicate the first two digits of the resistance value. Third color C gives the power of 10 for the multiplier of the value of the resistance, and the fourth color D gives the tolerance of resistance, which is 5% for gold, 10% for silver, and 20% for body color. This table lists all the color code of resistors. How to remember this? I used a mnemonic called BB Roy of Great Britain has very good wife to remember the colors of resistors. Note here, the first is B is black and the second B is brown. Now let's take an example. Consider this resistor with four color bands: blue, grey, green and silver. From the table we see that for the blue the color number is 6, for grey it is 8, for green it is 5, and for silver it is 10. We know that R is equal to A B into 10 to the power C ohm D. Now A is 6, B is grey 8 is 68 to 10 to the power C is green 5, less or minus D is 10%, which is equal to 68 into 10 to the power 5 less or minus. This 10% can be written as 10% of 68 into 10 to the power 5 into 10 by 100, which is 68 into 10 to the power 4. The whole thing by 10 power 6 into 10 power 6. 68 into 10 to the power 5 by 10 power 6 plus or minus 68 into 4 by 10 power 6 mega ohm. 10 power 6 is mega, which is 6.8 plus or minus 0.68 mega ohm. This is the resistance value. Let us now discuss temperature dependence of resistance. The resistivity of a conductor depends on temperature. For most metals, as the temperature increases, the resistivity also increases, and the change is linear over a limited range of temperature. This is mathematically given by rho is equal to rho naught 1 plus alpha T minus T naught, where rho and rho naught are the resistivities at temperature T and T naught respectively. The temperatures are taken in degrees Celsius and T naught is the reference temperature. Alpha is called the temperature coefficient of resistivity. Its unit is per degree Celsius. So we are going to calculate alpha. Rho minus rho naught is equal to alpha T minus T naught. This T minus T naught can be written as the change in temperature del T. So alpha rho naught del T is equal to rho minus rho naught, or the alpha is rho minus rho naught. This rho minus rho naught can be written as the change in resistivity del rho divided by rho naught del T. The resistivity versus temperature graph for a metal like copper is shown here. The curve is linear over a wide range of temperature. We saw earlier the resistance of a conductor is proportional to its resistivity. Therefore, the temperature variance of resistance can be written as R is R naught into 1 plus alpha T minus T naught. So, if there are two different temperatures, T1 and T2, we can calculate the resistances at temperature T1 as R1, which would be R naught 1 plus alpha T1 minus T naught. Similarly, R2, the resistance at temperature T2 is T2 minus T naught. On combining these equations, we can write an expression for temperature coefficient of resistivity. We can write R1 as R naught plus alpha R naught T1 minus alpha T. This can be written as R2 minus R1 is equal to, this gets cancelled, this gets cancelled. Alpha R naught T2 minus T1 is equal to T2 minus. So, the expression for temperature coefficient of resistivity alpha is equal to 1 by R naught into del R by del T. Let's say you have a conductor with resistance of 1 ohm at 0 degrees Celsius. If the temperature increases by 1 degree, then the temperature coefficient of resistivity alpha is equal to R2 minus R1. This property is actually used in making resistance thermometers, which measure temperature based on how the resistance changes with temperature. Now, when it comes to alloy like manganese, constantan, and nichrome, their resistance also increases with temperature, but the increase is much smaller compared to metals. This is why these alloys are used for high precision resistors wire. They maintain a more stable resistance even with temperature changes, making them ideal for standard resistances. Now let's talk about semiconductors like silicon and germanium. Their behavior is quite different. The resistivity of semiconductor decreases as the temperature increases. This gives them a negative temperature coefficient of resistance, meaning they become better conductors as they heat up. To recap, carbon resistors are cost effective and commonly used in general applications. Wire wound resistors are made from resistance wires and great for high precision and high power applications. Color codes help us to determine the value of and tolerance of resistors. Temperature dependence of resistors is crucial for understanding how materials behave in different conditions. So that's all for today. I hope you now have a clear understanding of types of resistors and how temperature can affect their behavior. Thanks for watching. If you like this video, don't forget to like, comment and subscribe.